I think it's time to start the afternoon session. I would like to invite Professor N. Haridas of IISc to chair the session.
So this afternoon we have two very exciting talks which will tell us whether quantum computing is likely to be a reality or remain a distant hallucination. So I request Michelle Simmons to give the first talk on quantum computing in silicon.
Thank you. What a great introduction and setting the sights high for me. So I'd like to thank the organizers for inviting me today. It's a very exciting time to be involved in research in the silicon field. So most of us in the audience will be fully aware of the ITRS roadmap and will know of Moore's law. And so the reason why this is an exciting time is if you look at this law, this is the scaling form of the law, where you've got a number of chip components versus the feature size. You can see that this law's been going for many decades, but around about 2020, it's predicted that industry will be taking up transistors of the size of single atoms. Now that's not that far away, and it's going to happen in our lifetimes. So this is really an incredibly exciting field to be in, because you can see that as industries scale down further and further, there's been many times over the last few decades when people have predicted this law is going to end. And indeed, for a long time, people thought it would never make it down to the atomic scale. So a lot of people started looking at different material systems, looking at gallium arsenide, looking at carbon nanotubes, graphene. But the thing that has amazed me is that industry has just kept going. They've put so much money into this material, they've understood it so well, that they recognize that they're going to take it all the way down no matter what. And so if we look now at an Intel transistor, so this is a cross-sectional SEM image of an Intel transistor at the 22 nanometer node, we can see now that these FinFET devices are essentially down at the kind of sub-10 nanometer level of the actual active component of the device. And I guess one of the things that amazes me is if you look at this kind of picture now, you can see that these transistors are no longer essentially a series of bulk materials with bulk material properties, but it all comes down to interfaces and surfaces. So what determines what happens in those devices really comes down to the atomic level. And so that really motivated me back in 1999 to move to Australia to get involved in this research. And really at the time I saw that across the world you could see that in the experimental field of scanning probe microscopy, people could actually manipulate atoms to make these beautiful quantum corral structures. And the question that I had was, why weren't people making devices in silicon at the atomic scale? And that's really why I moved to Australia to set that group up. And I guess the motivation for that was really to try and see how every atom in these transistors affects the device operation, to try and build these atomic scale devices using a scanning probe system and molecular beam epitaxy. And then really to look at these kind of fundamental physics effects, the impact of deterministic doping, seeing exactly what you can do when you control the interfaces and put every atom in position from the bottom up, recognizing that if you can put atoms from the bottom up in a design, you could actually make three-dimensional architectures that just don't exist with conventional top-down techniques. And of course, the ultimate goal, which was being set up at the time following Bruce Kane's proposal, was to look at the quantum computing using phosphorus nuclear spins. So this was his proposal. The two-level system is, in his original proposal, was the nuclear spin of a phosphorus atom in silicon. So there's the two-level quantum system. And I guess the critical thing here was that he actually worked out a beautiful scheme how to control individual nuclear spins using the hyperfine interaction, using this A gate above to control the overlap of the electron and the nuclear wave function so that you could actually flip individual nuclear spins by tuning them with these gate voltages. And then using these J gates to actually use the exchange coupling between the electron spins. So you could do nuclear spin, electron-mediated exchange coupling between these two nuclear spins. You could couple the nuclear spins. Now, the reason why Bruce, I guess, was a research fellow in Sydney at the time, why he was looking at trying to do this in silicon, there was these great advantages. You have these very long relaxation times. It's known to be many hours back in the 1960s. And this has really come about because you've got this low spin-orbit coupling. So the nuclear spins are really decoupled from their environment. In particular, the silicon host, the silicon-28, is essentially isotopically 95% pure. There's only 5% of silicon-29, which has spin a half. So you have this beautiful material system that's been engineered and purified for many, many decades. And the idea was if you could actually use this kind of technology that exists within the silicon industry, you could actually try and make these very small qubit-related devices. Oh, sorry. The disadvantage, however, is if you look at this, you can very clearly see that these phosphorus atoms have to be about 20 nanometers apart. You need individual gates to control the electron spins in each individual phosphorus atom, and you need these gates in between. So this really was kind of the ultimate limit of atomic scale engineering. It looked like a great idea, but back in the 1990s, people really just didn't believe that it would ever come to fruition. And that's really what the Australian group has done. Following that time, a lot of theoretical proposals came out. So originally it was the nuclear spins of the phosphorus donors. At the same time, there was this beautiful paper by Loss and DiVincenzo where they were actually looking at quantum dot structures. And there they proposed that if you go down to the last electron spin, you could use these as the quantum two-level systems. In the UCLA groups, they realized that they could also use now, instead of the nuclear spins, the electron spins around the phosphorus atoms. And by engineering different materials of different G factors, so using the silicon germanium system, they could actually put these phosphorus atoms further apart, and using these gate electrodes on the top, actually bring the electron wave function to a different G factor material. So shortly after that, in Australia, they started looking at the idea of using electron spins. The electron spin lifetime is still sufficiently long. It's much longer than the gate operation time. So the idea was you could actually use the electron spins instead of the nuclear spins. Then people started saying you could actually use donor charge qubits. You could actually have the electrons in one well or another well in a double phosphorus donor system. And then since that time, there's really been a plethora of different proposals. So there's been the singlet triplet qubit proposed in gallium arsenide systems, which will also be realized in the silicon system. There's been the exchange-only qubit, where you use three physical, in this case it would be phosphorus atoms, to make one single qubit. Very recently, there's been a proposal to use the valley states, so singlet triplet states in different valleys of the silicon system as the two-level quantum system. And then I think in the next talk you hear more about kind of the fast quantum dot hybrid qubit, where essentially you have two dots on one, two electrons on one dot and one spin on another dot. So really all of these proposals could all be realized in the silicon system. And there's a huge amount of effort to try and actually realize a lot of these silicon systems now. In all of these cases, however, the critical thing is you have to get down to the last electron. And so this really set off a huge amount of research across the world in the last 10 years, ever since actually error correction from 1990s. And in the silicon germanium system, they basically got down to the level of a few electrons a couple of years ago, so maybe 2008, 2009. In silicon MOS dots, you can take just conventional MOS transistor, and again, you can push down to the last electron. So people have been looking at those. In actual ultra-scale CMOS devices, they've now pushed down. They're looking at single electron physics in those kind of devices. And then there's a whole series of people looking at phosphorus donor systems. So here they're taking SOI nanowires, where they've got very low dope phosphorus, and again, they're pushing down to depleting to the last phosphorus donor or the last electron on these systems. And this is also true in the Australian group. So I guess in Australia we have two programs in the phosphorus and silicon route. One of them is to implant the donors with ion implantation into the surface and then recrystallize these. And typically what they do is they have a sprinkling of donors and they try and actually tune one of them into resonance to actually look at the single electron spin states of those. The actual system that I'm going to talk about mainly today is the scanning probe route. And I guess the key difference with the other phosphorus donor systems is here we're actually placing all the donors down on a single crystal silicon surface. And we're aligning to those individual phosphorus donors, we're aligning these A and J gates actually in the plane. So they're all patterned by STM in one step. And at the ends, we have our single electron transistors to be able to do the readout. So the critical part of this device is it's all epitaxial. So we have no interfaces or surfaces nearby. Once we put these atoms on the surface, we encapsulate with silicon by MBE, and we take those donor states away from the surfaces. So we get this nice, pure donor-like potential that we're going to use. Following this, we've basically had architectures designed by Lloyd Hollenberg, where basically he's shown how we can have interaction zones where we can do our couplings and our A and J gate operations. And then we have these qubit rails where we take them down to regions where we can do readout with the single electron transistor. We can actually use spin qubit by storing on the phosphorus nuclear spin, using that as a memory state. And he's come up with a whole architecture and a two-dimensional architecture of how you'd actually build a phosphorus and silicon quantum computer. And that really still forms the roadmap for what we're trying to achieve in the Australian group. So just to put us in perspective how it fits with other qubits across the world, I guess as I said, back in 1995, once error correction was known, a lot of people jumped in and started looking at gallium arsenide systems. They already had devices at around about 500 electrons, and they pushed down to the last electron in the early 2000s. In silicon germanium, they took up this challenge pretty quickly, and they got down to the last electron in around about 2007. Then I guess the phosphorus and silicon system has taken longer, and people always ask why. And the reason really is that you have to engineer these single atom devices. So you really have to be able to tune down to actually electrically address and then read out a single electron spin on a single atom in a device. And that's taken a lot longer to develop the technology, but I think in the last few years we've made tremendous strides. So one of the last reasons to motivate why you would want to look at phosphorus donors in silicon is to look at the T1 times. So here you can see the T1 times go up to 10 to the 3 seconds up here. These are the T2 times here. There's a function of carrier density. So this is all done in isotopically pure bulk measurements. And you can see that as you reduce the carrier density of these systems, you basically get larger and larger T2 times. And if you do a kind of modified Hahn echo sequence, you can push that up. even further. So you can actually get T2 times, again, of seconds in the silicon system. This is using the electron spin. Very recently in the Australian group, using the ion implant route, they've actually been able to measure the T1 time of 6 seconds and a T2 times of 200 microseconds after they've done the Hahn-Echo sequence. So all of these are really promising reasons why silicon is a good system to look at. And also, in addition to this, people have also looked at using the 31 nuclear memory, where they've actually been able to transfer spin information from the electron spin state onto a nuclear spin state and back again. And the nuclear spin memory time is about 180 seconds. So these are all very good reasons to be looking at the phosphorus in silicon system. So now I'm just going to go through some of the results for the STM devices and start off very quickly with the fabrication so people understand how they're made, then show you some of the kind of simple devices that we've made and some of the nice physics that we're seeing in these atomic precision devices, and then finally show you kind of where we're up to at the moment with some of the latest results in spin readout and spin transport and double dot devices. So very quickly, I know a lot of people in the audience have seen this before. So basically, the key thing about trying to make single atom devices in silicon is you have to use the scanning tunneling microscope to precision place them inside the silicon crystal. You can see it inside the microscope, but you can't see it outside. So that was one of the challenges to actually make atomic scale devices. The second challenge is it's not actually easy to manipulate atoms in silicon using a scanning tunneling microscope. You can't pick atoms up and place them somewhere else, as you would have seen in the quantum corral structure. So the covalent bonds are far too strong, so you actually have to make an atomic resist and then actually create a template with the STM where you can then open up holes on the surface and then use those as a template to put your phosphorus atoms in. So the key step is the registration markers. These are things you need to make outside of the STM, so you make them in a clean room before you put the sample into the system. You then come down with your STM tip with respect to these markers. You hydrogen terminate the surface, and then you dissolve the hydrogen with the STM tip to expose the silicon underneath. That's how you create the atomic scale mask. And these bright regions are where the hydrogen's been removed. You then bring in your phosphine gas, which only absorbs to the exposed regions on the silicon surface and doesn't attach to the resist layer around it. You then heat it up, and this is quite a critical stage because this encourages the phosphorus to go into the top layer of the silicon and to kick the silicon atoms out, and thereby they actually stay in place with 3 covalent bonds to the surface. You take it across to the MBE system, you encapsulate with low temperature MBE, so the phosphorus doesn't move. You can actually image that with the STM, you see them below the surface. And then using these registration markers, you take it out of the system, and then you make electrical contact to the buried device below. So the key part of this is there's going to be a few slides of chemistry about how you can make a single atom device. This is the silicon 100 surface that we use. These are rows of silicon atoms. If you look at the surface, we get these silicon dimer structures where there's this strong covalent bond that I talked about before, and these 2 dangling bond states of the surface. If we just look at what happens to phosphine gas, this is going to bring our phosphorus atom in. We see that phosphine likes to dissociate on the surface until eventually it sits in an end-bridge site, and we heat it up, and it goes in and forms a silicon-phosphorus heterodimer. Now, the critical part of this is we need to open up exactly 3 adjacent dimers on the surface to allow this chemical reaction to occur. So we have a little movie here showing this chemical reaction. Here's our phosphine molecule. You can see that the hydrogen goes to one side. The other hydrogen comes down to the same side of the silicon dimer. The other one goes across to the other side, and then the phosphorus atom will go in through this end bridge site and kick the silicon atom out. So if you can open up a hole that's exactly 3 dimers wide, you can deterministically put that phosphorus atom in with plus or minus 1 lattice spacing. That's how we get our qubit states in here, but we also, as I mentioned before, at the same time, we align these gates on the surface to that phosphorus atom. And we do that essentially by opening up large regions of the surface and phosphine dosing those at exactly the same time. And the critical part of this is understanding the chemistry to get a very saturation dose surface so that when we heat this surface up, we typically find that 1 in 4 of the phosphorus atoms is replaced by 1 in 4 of the silicon atoms is replaced by the phosphorus atom. So this is an incredibly high density, and this was, I guess, unexpected when we started. We didn't realize we would get such high densities on these systems. It basically means that the average separation of the phosphorus atoms is less than 1 nanometer, and the Bohr radius is 2.5 nanometers. So wherever we put these phosphorus atoms down at the high density, we create these local metallic states inside the semiconductor. And these metallic states are going to be used as our gates. So they're epitaxial gates, single crystalline gates that we bring in. The other interesting thing is in the same way that we've got very abrupt confinement in the vertical direction by dosing on one atomic plane, we also have very abrupt confinement in the lateral direction with the STM patterning. And this is something that, independent of the quantum computing project, the industry is very interested in for making ultra-shallow junctions, and that's another project that we have going in the group. So what does this do? What does this abrupt doping do? Now, Shankar talked before about our 6 bulk degenerate values in silicon. when we have this very abrupt doping in the vertical direction, we basically break those valley degeneracies. So we end up with 4 delta valleys out of the plane and 2 gamma valleys in the plane. And because we have essentially this very high doping, what we find is we get an impurity band that comes down below the Fermi energy. So you can see here's our 1 gamma, 2 gamma, and 4 deltas. So because of the very strong vertical confinement, we get valley splitting of these gamma states here. And this valley splitting basically is of order of tens of MeVs. And that's basically what we're seeing up here. So it's basically an impurity band that we bring down below the Fermi energy. And essentially all of these bands are occupied because of the very high doping density that we have. So what does that mean for the semiconductor? It basically means that we're basically conducting here through a very highly disordered system. The phosphorus atoms are sitting in the plane of where the electrons are traveling. As a consequence, the mean free path is about 5 to 10 nanometers. The phase coherence length, on the other hand, is very long, so it's around about 100 nanometers at millikelvin, and KFL is around about 30. So you've got this highly conducting metallic state, which is essentially a disordered metal, which is where we're going to be passing the electrons through. And because of the high doping density, essentially the electrons are screening the potential charge of the positive phosphorus atoms beneath them. So it's unlike any kind of highly conducting system. It's like a dirty metal. So now what do? We come along with our STM tip, and we're going to basically pattern those phosphorus atoms into the surface in any kind of structure that we want, all the way down to atomic scale. And so one of the first devices that we tried to make was just a simple quantum wire structure. And we designed this device really to show us how the conduction in the device worked, to show us this kind of phase coherent effect. So if we look at the conduction, we basically pattern 2 devices at the same time. We're looking at their magnetoresistance here. This is our 90 nanometer wide wire by 900 nanometers long and a 4 by 4 micron square. And as I said before, these crosses basically represent the phosphorus atoms where the electrons are traveling through. You can see as the electrons come through, they scatter off the phosphorus atoms and they form these phase coherent loops. And you can see the signature of this weak localization in the magnetic field data at 4 Kelvin. And if you fit this to the Hikami formula for disorder conduction, you can extract the phase coherence length of about 38 nanometers. So you can see whether you're in this square structure or this wire structure, you form these phase coherent loops very nicely. If you now cool it down to millikelvin temperature, you can see the difference between the 2 devices. You see basically as you reduce the phonon scattering, the resistance goes up. You form larger and larger of these phase coherence loop and the resistivity increases. And as you apply the perpendicular field, you break the phase coherent backscattering. If you now fit this, you see that the phase coherence length is about 131 nanometers, which is easy to form in these square structures. But in these wire structures, which are only 90 nanometers wide, they can't form these phase coherent loops. So you get this saturation of the resistivity at a lower field value. And if you look at the magnetic field value at which these 2 deviate, you can work out what the magnetic length is and then the width of the wire, and it comes out to be 93 nanometers. So this was really the first time that anyone had measured something where they'd actually seen lithographically where the dopants were placed, and they could independently confirm it using electrical measurements.
What's the temperature of the high temperature one?
So 4 Kelvin and millikelvin, 50 millikelvin. Sorry, it used to be up there. So now what we did was we basically went to make these wires thinner and thinner. And you can go all the way down essentially now to where the wires are essentially 2 dimers wide, so literally 4 silicon atoms wide. And you start to see now that the chemistry again comes into play. The phosphine likes to dissociate along the dimer row and not perpendicular to the dimer row. And as a consequence, you get lower resistivity in these structures where you basically pattern the wires along the dimer row. But the interesting part now is if we measure the resistivity of these wires as a function of the diameter. These are the red stars that you see. You can take it all the way down towards the atomic scale, and the resistivity stays the same. Now, this was really, I guess, unexpected at the time because a lot of people were measuring silicon nanowires and finding below about 10 nanometers, no matter how much they increased the dopant density of their structures, the resistivity shot up to infinity. And so try and understand why this is happening. The key difference with our devices is that we have this incredibly high doping density where the wave functions are essentially overlapping, so they're so close together that you form these extended states. But the other critical thing is these devices are then a long way from the surfaces, so they're encapsulated with silicon. So as a consequence, they're not interacting with surface states. They have a dielectric, which is essentially a long way away. The silicon oxide is a long way away. So basically, you don't deactivate the carriers as you do in the other kind of freestanding nanowires that are out there.
The phosphorus probably are ordered also.
So they're not completely ordered. There is some ordering, but they're not completely. So basically it's a gaseous chemical reaction. So you can't actually put them down unless you create holes to put them exactly in position, which is something that you can do. So this, I guess, was a very interesting result. It basically shows us that we can make these wires very, very thin and bring them in towards our single atom qubit states to address them. So now I'm going to go into some more complicated device structures where essentially we've made a quantum dot architecture. So we have a dot in the middle here with about 4,000 phosphorus atoms, our source and drain. We've got a plunger gate here that changes the occupancy of the dot. And there's two gates here that control the tunnel barriers. And you can see on the right-hand side the atomic rows underneath. So you can see the kind of atomic precision in those devices. If we now measure the conductance through these devices, we get kind of standard Coulomb blockade. And if we look at our kind of stability diagram by changing the source drain bias, again, we see these beautiful resonances that come in. So we've got a fairly large number of phosphorus atoms and therefore electrons on these systems, again, with a small charging energy. And we can use these in-plane gates to deplete by about 50 electrons on these quantum dot structures. At the time that we first saw this, it wasn't obvious what was giving rise to these resonances. And so since that time, we've looked at lots of devices, and I'll show you in the next few slides how we work that out. But one of the nice things about these phosphorus and silicon devices is that essentially where the phosphorus atoms are, it's very strongly pinned, the Fermi energy. So you can take these devices and remeasure them many, many times, and you essentially get the same result every time. You can warm them up to room temperature, cool them down again. You can even put a gate on top of them once you've already measured them in a dilution fridge. So this was a result with the in-plane gate. We took it out, we put a surface gate on top of a native oxide, so it's not going to be a good gate. And using that top gate, we could go back and we could measure the Coulomb oscillations again. And you can see the key difference here. This is an epitaxial gate, and this is a gate that's sitting on an oxide. So it's hysteretic and it's noisy. And one of the things that, I guess, from this result we were interested in was to start actually looking at the noise. So we started up a collaboration with Arindam here at the IISc, where basically we're looking at the 1/f noise, the low-frequency noise. And you can actually characterize the noise in these systems by something called the Hughes parameter. It's a phenomenological parameter. And I don't know if you can see, but these are all the different silicon devices that existed in the literature. And for the highly phosphorus-doped silicon down here, you can see that the noise is much, much lower. In fact, it's 6 orders of magnitude lower than for bulk phosphorus-doped silicon at the same density. And I guess this is something that Arindam and I are still working on. We have a poster out there that I encourage you to see with the student Saqib. And basically, we don't understand fully why the noise is so low in these devices. So they're very heavily doped devices, and yet the noise is much, much lower than other silicon devices that have been seen. But that kind of bodes well for basically minimal charge noise in these qubit devices. So now we're trying to understand what gives rise to those resonances that I showed you in the stability diagrams. So we're making our devices much smaller now. So we've reduced the size of the central dot, where we know we basically, from the exposed area that we know we have 3 adjacent silicons to get 1 phosphorus atom in. We have basically 6 plus or minus 3 donors in this small quantum dot structure that I'm showing you. And again, if we now look at the stability diagram of these structures, we can see it's very similar to before. We have these strong resonances that I showed you earlier. Except now that our Coulomb diamonds are actually increasing in size as we make the gate more negative. So we're essentially reducing the electron number on the dot, and we're increasing the charging energy, as you might expect, as the physical size of the dot is changing. But the key thing we're interested in is to try and understand what's happening with these resonances. If you zoom in, you can see these resonances are separated by about 100 microeV. So I guess this was really unexpected. We've made this very small quantum dot structure. And you would know that as you make things smaller and smaller, the quantum energy levels should be further and further apart. But we're finding that we get these energy levels that are incredibly close together. So you can look at the mean energy spacing that you would expect just from the size, the physical size of the dot. And you can work out that that should be about 12 millielectron volts. You can also imagine what happens to the leads. And I guess one of the key things now is, unlike most quantum dot architectures, where you've got 2-dimensional reservoirs connected to a dot, we've actually got 1-dimensional leads now because they're so thin. So either side, you've got these 1-dimensional density of states in the leads interacting with the quantum dot states. But again, because from the SDM we know the dimensions of the leads, we know that the separation should be around about 7 MeV. So you've got these two effects giving you MeV energy levels, and yet we're seeing 100 microeV. And that really now comes into play where we have to understand what happens to the band structure when we very strongly confine, not just in the vertical direction, but in the lateral direction. So I showed you before, when you make these delta dope structures and strongly confine them vertically.
Sorry,
Yeah.
I'm not familiar with this. So in the Z direction, what is the level of confinement that you have? Where are the electrons residing? Close to the phosphorus atoms?
They are, yeah. So they're basically, there's one extra electron, but they're basically hanging around where the phosphorus is. And
sideways, what is the, how?
So essentially, in the physical limitation, we see that they're basically 1 or 2 lattice spacings from the plane that we put them on. But then, of course, we imagine they've got like a Bohr radius around them. So it's of order about 1 or 2 nanometers spread from the Bohr radius electronically rather than their actual physical separation. So you've got this very, like I said, very strong, good question, vertical confinement, which basically breaks these 6 degenerate values to the 4 deltas and the 2 gammas. But we now because of the valley oscillations, we get this breaking in the vertical direction from the strong confinement. But now, because of the STM patterning, we're also very strongly confining abruptly in the lateral direction. And that basically means that we also get valley splitting here in these delta bands. So the key thing is we've got these very highly doped structures. So in this dot where we know that we've got 6 plus or minus 3 phosphorus atoms, you can start to populate these valley states with the electrons. And you can see you can put 4 in here, and the remainers would go in these delta bands up the top here. There are actually 56 different possible ways you can put these 3 electrons into these delta band states. And if you work out, as we did with Mark Erickson and Mark Friesen from the University of Madison, Wisconsin, what the energy level separation would be for these kind of very strongly confined dots, you can see that we're now starting to get towards this 100 microeV energy level spacing. And indeed, if you take into account the anisotropy of the physical size of the dot, you see the average energy level spacing is about 100 microeV. So the critical point to take away from this is when you strongly confine things in both the vertical and lateral dimensions to create these very, very small quantum dot architectures, then you have to take into account the valley splitting. So valleys are very important in silicon.
What about the exchange energy scale that Shankar was talking about?
That's right.
How large is that?
Well, so the exchange energy is something that, as Shankar's mentioned before, is an oscillatory effect if you have it in the bulk situation away from electric fields. So one of the key things I think that's happened over the last 10 years or so is there's been a lot of discussion about the exchange energy. And basically the idea is really you have to have some kind of electric field around that in order to be able to minimize those exchange oscillations. And I don't know what you think, Shankar, but there's no agreement, I think, at the moment about whether they're going to be an issue or not.
Well, I mean, we know that valleys must be split for silicon to work.
Yeah.
And you only work with valley split structure. And I think the quantitative aspects have not been worked out yet. But everybody accepts after work that you must have valley splitting. You don't have valley
Oh, yeah,
splitting.
absolutely.
And there is valley splitting here, so,
Yeah.
I was wondering whether the exchange energy scale is of the order of 100 UeV, or that's separate.
No, so it's larger than that.
No.
It's not.
Yeah. So it's separate.
It's hardly larger than 100 microvolts.
Yeah.
Sorry, Michelle, you're saying that now all the degeneracy has been lifted totally, or it's not degenerate, 4-4 degenerate?
So I guess because when you're looking at the single donor states, you're going to be looking at the gamma 1 and gamma 2 states here, which are split, yeah? So when you take it away from those high density states, you basically are sitting in these bands here. And that's I'll show you in the next couple of slides. So I guess this was a 7 donor system. And I guess the key thing now is to go towards the single donor system. And hopefully this movie will go quickly. So this is really just the full fabrication of how we do the single donor. There's our registration markers. We zoom into the atoms on the surface. We hydrogen terminate. We come along with our STM tip and we deliberately open up these 6 holes. The thing that we've realized now is that we have to really saturation dose this central region to force 3 pH2s into that central region. And then as we do this, we actually force a chemical reaction to occur when we heat this up. So what you find is pH2 likes to grab a hydrogen and come off the surface. And in doing so, when it does that, it leaves a hole for the pH2 here to dissociate. This will then grab with this pH2 and leave, and that allows this phosphorus atom to go in through that end bridge site. So this is a chemical reaction where you can actually control where the phosphorus goes in, and the signature is you get this ejected silicon atom. So that really shows you in the STM imaging what's happening. We then get rid of the hydrogen resist, and we encapsulate with silicon, and that gives us this nice crystalline environment for the qubit state. But the critical part is when we open up that hole to put the single phosphorus in, as I mentioned before, we open up these lead states, and we saturation dose these at the same time. And once we zoom out, you'll see that those lead states are registered with respect to the registration markers on the surface, which we then use outside to put aluminium contacts down in a conventional clean room using EBR. So that's how we make the single donor. That's actually the hole that we've opened up with the resist technology. And this is the actual ejected single silicon atom that's come out once the phosphorus has gone in. So with the STM, you actually image it in the whole fabrication process. So you know exactly where it is. And I guess the key thing then is you've got to get that through the clean room to put your contacts down without killing the device, which is always the hair-raising moment for the student. But then at the end of that, you end up with this beautiful stability diagram. And this stability diagram basically only has these 3 diamonds. So you have the D0 state, where you have the phosphorus with 1 electron sitting on it. You can remove that electron to give you the D plus state, and of course you can't remove any more. Or you can add another electron to form the D minus state. And that really is the characteristic signature of what a single donor in silicon should look like. And if you cool that down to millikelvin temperatures, you can actually measure the charging energy here. And the key thing about the charging energy is exactly what you would expect if you look at optical spectroscopy measurements of a single phosphorus donor in bulk silicon. So here you see that the transition here is about 43.9 MeV, And here what we're measuring is about 47 plus or minus 0.2 MeV. The other thing is you can actually look at the excited states here. They're mixed in with the one-dimensional density of states that I talked about before. And again, you find that the excited state energy levels match. But I guess one of the key things you can see here is if you look at zero gate bias, the donor is already ionized. So you have to go to about 450 millivolts to actually get the electron to sit on the phosphorus atom. And one of the things we worked with Gerhard Klimek's group was to look at the electrostatic potential that the donor is sitting in and see if we could understand why it takes 450 MeV. So he used essentially these three-dimensional self-consistent calculations to work out what the potential is around the donor with the different gates around it. And then he superimposed on that the potential that you would expect from atomistic calculations for the single phosphorus atom. And you can see that as you look across here from the different gates, gate 1 to gate 2, and across the source drain direction, you have this anisotropic potential that the donor is sitting in. And you can compare this directly to what you expect for a single bulk donor in silicon. And one of the key things you see is the D0 state here. This is the state at which you have the electron in the donor is actually sitting up here above the silicon conduction band. And that contrasts strongly with what you expect for a bulk-like phosphorus donor in silicon, where it's sitting 45 MeV below the silicon conduction band. And so we actually worked with him to try and figure out what happens as you apply a gate bias to this D0 state. And you can see as you apply the gate bias here, down the bottom here, you can see this D0 state moving down until it crosses the Fermi energy. And that is the point at which you would get the occupation of the first electron on the donor. And it matches beautifully with the experimental results. You can then put in the D minus state up here, apply a gate bias to that, and see at what point that crosses the Fermi energy. And here it comes out about 720 MeV, and we measure about 800 MeV. So this is really beautiful. We've really understood that we can put that phosphorus atom in a silicon structure. We can understand the electrostatics of the environment, but we find that basically the phosphorus donor behaves as if it's a bulk phosphorus donor in silicon. It has exactly the same energy level structure. So now what we want to do is to read out the spin state of that phosphorus atom. So we pattern next to the phosphorus atom, using the STM technique, a single electron transistor. So here is our single electron transistor. Here are these phosphorus atoms. We think we have probably about 4 in here, in this small structure here. And what we're going to do now is modify the gate 1, gate 2 direction, gate biases on those, and look at the Coulomb potential across here. So we're going to stick on a Coulomb peak and see at which point we can actually get the energy level of these phosphorus atoms to align with the island of the SET, to see if we can actually use this for spin readout. So here we have essentially the gate 1 versus gate 2. These are the 2 gates either side. And you can see, if we look down here, we have these transitions. And these transitions are essentially the electron number changing on that small phosphorus island. And if you zoom into one of these transitions, you can see that when an electron moves from the phosphorus island to the donor, to the island of the SET, you get this discontinuous jump, and you get a shift in the potential of the Coulomb blockade. And we're going to use this change in potential now to see if we can measure the spin state of the phosphorus atoms on those 4 electrons. And the way we do this is using this kind of gate pulse sequence that was developed by Eltzman and published back in 2004. So we put our phosphorus atoms inside a magnetic field, and we split the spin up and spin down states with respect to the island of the SET. We're now going to pulse down so we come off resonance of the SET, and we're going to load an electron. If we load it into the spin up state here, you see that the current through the SET drops. We're then going to pulse it to the readout position. If it's in the spin up state, it will move on to the island of the SET, and the current will go up, and the electron will move back. And you basically see this peak in the current as the electron spin has moved on and off the island. And if you now pulse the electrons back up here, you can actually get them to leave the dot onto the SET island, and you go back onto resonance of the Coulomb blockade. So this is the signature you would expect for a spin up. We can also do the same thing now, but instead of loading spin up, we load spin down. If we now pulse to the readout position, because it's at a lower energy than the SET island, it can't move across. You have to pulse it back up again above the SET island energy for the electron to come back off. So this is the signature of a spin down. And basically, you repeat these measurements many, many times, but once you've loaded the electron, you actually increase the wait time. And when you increase the wait time, you basically cause the electrons that are in the spin-up state to gradually decay to the spin-down state. And as a consequence, you can extract the T1 lifetime from these, which comes out to be about 2 seconds. And you can plot this as a function of magnetic field. You get this characteristic behavior, which is essentially limited by the spin lattice relaxation mechanism caused by valley depopulation. So the key message here is that in these phosphorus electron spin states, you get these very long relaxation times. And this was also published in 2010 on the ion implanted devices, where you can see here they had spin relaxation times of about 6 seconds. So the last thing that I want to leave you with is our comment, I guess it's about 1.5 years old now, of our measurements of making 2 donor devices. So one of the promises of the STM route eventually is that you can actually pattern multiple donors fairly easily with the STM. And I guess one of the challenges of those devices is you imagine they're very, very close together. So they're order of 10 nanometers apart. So you need these gates to be able to control the electrostatic potential so you can actually transfer electrons from one donor to another. And I guess when we first started out trying to do this, we actually put these gates in what was an intuitive orientation. So we've got our phosphorus donors sitting here between source and drain. We've got gates which we've kind of aligned to address each of the phosphorus atoms. But when we looked at these stability diagrams, we saw that we had these very strange kind of distorted honeycomb diagrams. And this is not at all what we were expecting. I guess on reflection, it was actually pretty easy to understand what's happening. Essentially, this gate here is not only changing the electrostatic potential on this dot here, but it's also capacitively coupled to this one. And so that's the key problem when you have it in this linear arrangement. So we actually change the angle of the phosphorus atoms with respect to each other. So this gate will preferentially couple to this one, this gate will preferentially couple to this one, and the cross-capacitance term here will decrease. So this is the direct capacitance, this is cross-capacitance. And obviously we want to make sure that we don't have parallel tunneling going through both dots at the same time. So we chose an angle of about 60 degrees as the optimal angle, and then we actually made that device and found that we got a lot better results than the previous one. So here's the angle sitting at about 60 degrees. And it was around this time that we realized that we could start using a program called FastCap, a capacitance modeling program, which combined with Simon electronics modeling program could actually predict from the STM patterning. So literally just using the capacitances and the resistances we would expect from these structures, what you would expect to get in the stability diagram. So this is the prediction that we expect, and this is the actual measurement at the end of the day. And it was really at this point that we realized that we could use these programs in the STM mode because we know exactly where the phosphorus donors are to actually to actually predict exactly how to place our gates and our donors with respect to each other on the surface. So since that time, we've now reduced it down to the level where we have these two single phosphorus atoms sitting on the surface. Again, we look at the stability diagram in the modeling, and we can see that we basically just, with this gate range that we have, we just basically get from the 0,0 state to the 1,1 state. That's what we measure experimentally. And you can actually see that you deplete both of the phosphorus atoms of electrons in the gate range. And you can put one electron to one dot, one electron to the other, and two electrons, one on each dot. And the interesting thing about this, again, is if you look at the energy or the voltage that we have to apply to get the electrons to occupy these systems, again, it's about 450 millivolts. So it's exactly what we expect with a single donor. And we can actually look at, again, in a source-drain bias, we can actually measure the energy levels. And we find the energy levels are very consistent with what we would expect for a single bulk phosphorus donor in silicon. So the key exciting part about this is we're now making double dot devices. And these are devices that I didn't have time to talk about. These have all been produced in the lab. We're now putting an ESR line on the surface to be able to do spin rotation. We're looking at singlet, triplet qubit states. We've got 3-dot devices with 3 single phosphorus donors in there. And we've also now started to realize devices where we bring in our gates in the vertical direction. So I mentioned before we can pattern in one plane, grow silicon, and pattern in another plane. So you really get these 3-dimensional architectures underway. So in summary, what I hope to have gone through very quickly is our results for making these very narrow conducting wires in silicon, being able to do the first single atom transistor with these atoms placed with atomic precision. We've been able to read out the electron spin states on these, and currently we're investigating spin transport in double and triple donor devices, and systematically working through to make essentially our 5-year goal, which is a 10 phosphorus qubit silicon, phosphorus in silicon qubit system. And with that, I'd like to thank the research team. We've had a fantastic group of people and our funding agency. So thank you very much.
Thank you very much. So we have time for some questions now. Yeah.
What's so magic about 60 degrees?
So really 60 degrees is just the angle at which you can get the best direct capacitance and the minimal cross capacitance, but you also minimize tunneling through both dots at the same time. So you could probably still shift it like 10 degrees either way and still get a working device, but you basically want to be able to get as many transitions in your gate space as possible.
Okay.
And I think one of the key things is every time you add a gate or a single electron transistor, you change the electrostatic potential profile and you have to re-optimize the gate space.
Hi. I had a question about the tunnel gap. So tunnel barriers that are there for your dots that you have induced near the phosphorus atoms. So in all of your images, their tunnel barrier width is about 10 nanometers. That's a little bit thicker than what we imagine, because you're saying that the electrons are fairly tightly confined close to the phosphorus atom.
That's right.
So, I mean, do you think that's an issue? Because
so so it's an issue that it's too small, or
I mean, it's too thick a tunnel barrier. Typically, the tunnel barriers are much thinner.
I don't see that it's an issue, no. So you can control, I guess, with the in-plane gates, you have some control.
What I mean is, can you get them closer? Because in principle, if you have an STM, you should be able to get them
Yes,
much more.
yeah. You can get them anywhere you want them, basically.
Okay.
So I guess the 10 nanometers is what we're finding gives us the best gate range and the best capacitive coupling at the moment.
Okay.
That's also the size of the wave function. It's
Again?
not tight. The extra electron is not tightly bound. It's an impurity state.
It's an impurity state. So
10 nanometer.
yeah. So the Bohr radius is about 2.5 nanometers.
2.5.
Yeah. So it kind of floats around where the phosphorus is.
So there's been some work on silicon quantum wells where people have shown that the Valley splitting is actually dependent on the field, on the magnetic field. Do you see this in your dots? I mean, do you see the spacing change with magnetic field, perpendicular magnetic field at all, or does it not affect it? Or?
So I guess most of the studies that we've done are at the single electron level.
Right. So it shouldn't really make a difference at all.
So it's not an issue there, yeah.
These are different systems. Quantum hole is an electron gas. It's a localized electron system. Physics is going to be something different.
Yeah, I mean, the Valley splitting is a very old question. People have been studying it for 50 years. And the splitting, of course, depends on whether you're looking at electron gas or electron, and it's very difficult to actually calculate theoretically. You have to study it.
So I think one of the advantages of the donor system is that you get the potential profile for free. And so you don't have to use many gates to create the quantum dot structure. And so that's one of the advantages. But the disadvantage is that you have to engineer everything pretty much with sub-nanometer precision. So a lot of time is spent designing the devices before you make them to make sure that you get all the right gate ranges and the capacitive coupling. And then once you get that design right, it's actually pretty easy to make them.
How far are you from beginning quantum computation?
So that's a very interesting question. So I get asked this a lot. So I guess if you think about it, originally, if you look at the conventional transistor, so the first transistor was, 1947, and the integrated circuit from that time was about 15 years away from that first transistor. So we're kind of at the first transistor stage with the quantum computer. And so 15 years, I think, is where we're going to be to get something like a 20-qubit system.
Will it be 15 or 150? Because
Hopefully we won't even be 15, to be honest.
So many people are working, it may be 1.5 years.
So many people are working?
It's in this field now, compared to olden days. So
Yes.
progress should be faster.
Exactly. That's my thought. So it was 15 years before. It should be more like 10 years now.
Are there any other questions? If not, let us thank Professor Simmons for this wonderful talk.